All right, so today we'll be talking about what is called tensor functions. And already mentioned that before that a scalar function can be, okay, so even being, also it is a scalar, as in this case, some scalar f, can be in function of a higher order tensor. For example, this case would be second order tensor A. And one of the examples was that we already mentioned is, for example, the energy, the elastic energy that is stored in a deformed material when energy would be a scalar, while that can be a function of a second order tensor that can be represented by, for example, by strain tensor, right? That describes deformation. Now, in the spirit, then so there is a dependence of A on A, and one of the ways I would typically characterize how much the that function changes with the argument as A, for example, changes. One of the way how we do that, we actually use the derivative, right? So if that would be just function f of x, so we could take the derivative df dx, and that will characterize it to some extent the rate of change, right? Now, so can we do the same here for this so-called scalar tensor function? Well, in fact, yes. So in general, we should be able to be able to do so and take the derivative of f with respect to its argument to that second order tensor A. Now, this is a little bit unusual for us, as we are trying to take, we basically are dealing with scalar, but now we are taking taking the derivative with respect to higher order tensor to second order tensor. So this is a little bit unusual. Also, we did do that before, not in this course, but I'm just relating to other courses that you've been taking, is that we took the derivative, for example, with respect to a vector, right? So when you, in a way, when you think about calculating the gradient, right, in a three-dimensional, two-dimensional space. Now, all right, so we are interested in such situation when we want, again, making a physical example of that, so we want to see how the, for example, energy scalar changes as we change our, for example, strain tensor, whatever it is, right? So just for sake of the discussion. So we will do the following steps to actually to try to calculate that. So okay, so we'll start from calculating the full differential of or increment or small change in our function f, and the way to do that is the following, right? So so we write df, and then we have the partial derivative of df daij. And so these are, of course, the components, right? So of aij, and these are daij, the components of the differential or change in the tensor dA. Now, the components of that dA we can obtain as usual we do through writing this dA as a tensor and then projecting that to our dyadic product of ei ej. So that will give us these the components of that. And so so we are making our projection operation, that's as we usually do with dot product, right? So in the result of the dot product, so this ei tensor product ej is one second order tensor, and dA is another second order tensor, and so the double dot of this, or the double dot product, or double contraction, or so that will result in basically produce us the components of that, so which is so these are of course scalars, right? So dA aij is that our basic definition that would work for any second order tensor. Now with that, so now we can go back into the previous formula and just simply substitute these results that we obtained the aij, this trivial result of the projections, right, and can write it right in here. And so then we'll still have this part here, this is the partial derivative of f with respect to aij, and explicitly writing the the components of the differential of the change in aj. And so right, so we substituted that, we just took that whole thing and put here, and our result is just like that. So then based on that, we can say that the derivative of f with respect to dA, so our initial derivatives that we were after can be written in a, so basically by using the structure, so can be written in the following way. So we just define that this will be our derivative of a scalar tensor function with respect to a second order tensor. So that will have this structure, right? And in that way, so we know that we need to take to calculate each component of that new second order tensor, right? And again, so here what we should note is that we start from a scalar, but once we took the derivative with respect to second order tensor, our result will be second order tensor. That manifests here in the existence of this dyadic product of this of these two, because this is obviously the basis for a second order tensor. So EI tensor product EJ. And now the components are simply, so again, the components are scalars that you can think about them as building the matrix IJ. So this we just take that scalar, the same scalar, and takes the derivative with respect to each component of AJ, and that will build us that the component of the matrix of components, if you like. And to make it an object as a tensor, so we'll have this EI EJ notion. Okay, and so now with this definition in 149, we can extend that to any higher order objects, right? So now we can think about a situation when we have another tensor, let's say second order tensor for sake of discussion, that depend on another tensor, right? So, and again, an example of that would be stress tensor that would depend on a strain tensor, right? So this is quite possible. So we may want to know the dependence between them and characteristics of their changes. Now, again, just for an example, and to make a fit connection of these abstract creatures and objects to some physical meaning. Now, let's define, let's say, kind of generalize this for higher order creatures, right? So we can now produce by this operation a higher order for in this particular case, when we take a second order tensor that depends on another second order tensor, so the result will be a fourth order tensor, right? So let's follow this a little bit by smaller steps and see how it comes to this structure, right? So if we go back, so all right, so here's our dependence again of let me just again with the pointer. So here's our second order tensor A, which appeared to be somehow dependent on another tensor, second order tensor B, and so the or may not depend. If it doesn't depend, still the result will be fourth order tensor. It's just the components of that will be all zeros, but still this operation would produce a fourth order tensor, so that B. Now, so basically we're using a similar structure, just as we wrote for example, for just here in 149. So when we take a derivative of something with respect to A, that will be derivative, that partial derivative of that something with respect to components multiplied by this tensor product EI, EJ, right? And so the only difference in this formula is that instead of F, we actually have here the second order tensor A, right? So now we can go ahead and write this A in a explicit way, how we can write this in terms of the components. So well, and the usual structure of a second order tensor would be the components, the scalars, that are multiplied by a similar tensor product here of the basis vectors, dyadic product I and J. The only thing is that I and J is already taken, and right, so that's and we don't want to confuse this notation even more. So we need to make sure that when we expand and write A explicitly, so we use appropriately different indexes. So and here, for the sake of this discussion, so we typically for whatever reason the most popular indexes are I, J, and then there are sometimes I used KL and MN. So and very rarely you will see something else if we exhaust what the set that is most popular. So so we decided, okay, so MN, so that's the choice, right? So we basically wrote AMN. So in this is our AMN, right? And the derivatives that we need to take is only we're not taking the derivative of MN here. So the dependency is of course in the component. So that's our definition, right? So that's how we're taking this derivative with respect to second order tensor. And so okay, so well, as you can see now, so there are three tensor products, so it's four components then like that, and so you can obviously conclude that the result of that is the fourth order tensor. So once you see that you're taking the derivative, and that of course makes sense in terms of the dimensions of what happens and dependencies between different components. So if it takes the derivative of second order tensor with respect to another second order tensor, so the result is a fourth order tensor. Now, and okay, of course, this is the structure, so we can even continue that and start taking the derivative of fourth order tensor with respect to another second order tensor, and that could be an interesting exercise, but we probably will stop with this here. So for us, that would be more than enough, what we want to use in the continuation. Now, one more example of the situation, and an interesting one that is worth looking in is is that. So what will happen if I'm trying to take the derivative, and very useful particular case when I'm taking the derivative of A with respect to the same tensor A. So I'm not having here B, but I have A, right? So there will be some components that will be the same, so that will be producing us non-zero values, but there will be some components that don't depend on others in no other way, and so then that will produce a zero, right? So there is a first notion that some components will be just one, and some components that will be just zero for when the indexes of the components don't match, right? So, okay, so that's already something reasonable for us to expect here as a result. Now, okay, so we already given formula 140, so of course we can use 140 for this case as well. So it's just a particular case of homogeneous case of the derivative of tensor with respect to another tensor. And so we can just write that, and of course, so that we'll have dAm n with respect to dAij. And of course, this is our basis for the tensor products that constitutes the object of fourth order tensor. Now, the only thing that we now can take care of, because now the dependence of A on A is known, right? Because it's basically the same function, but it's not always one, because some components are clearly independent. Well, in that case, we couldn't continue because nobody told us how these components are related. What is the dependence of these components of Mn on Bij? So in this case, we can actually conclude that analytically, right? So they will be non-zero when the indexes here will coincide. So we need to make sure that M and I are the same and N and J are the same. Then in that situation, that will be non-zero component. That actually will be 1, and that produces the known for us the structure for Kronecker delta. So exactly when M and I are the same, and then we have the result equal to 1, and when they're different, it's 0. That's exactly delta. So we will have 1 delta Mi, but we also need to make sure that N and J are also matching. So we'll have another delta that will say that when N equal to J, so multiply it by 1, right? And as a result, we have this multiplication of two deltas Mi and J. So and in that way, you can introduce the a different structure for higher order identity tensor, right? So we had second order identity tensor, which had only delta, 1 delta, but here we have fourth order identity tensor that also can be used. But again, this typically the fourth order identity tensor is not that common to appear in your derivations, and typically you would just would introduce it, you would define and introduce it explicitly if you want to use it, because it's less common than the second order identity tensor that is directly related to the components in terms of defined in terms of Kronecker delta. Now, one more trick that is interesting to look into, and a question to ask: will you expect this result, this structure, to change? So for the components that being delta Mi, delta Nj, if, for example, I would say that A is symmetric, right? So if the component, if I can change Mn, and what would be the result? And this is a good probably point to just for a few seconds, maybe to pause that a little bit and contemplate a little bit of what you would do to actually to have the result, and maybe the result will be a little bit surprising here. Okay, so the question is how this will change, or will that the 151 change if we know, if we use that A is symmetric. Okay, so that's all right. So well, just a reminder, what it would mean that is symmetric is that we can basically write A as a sum of this original form plus the transpose, and then multiply it by factor half to make it the original one, right? So the only symmetric part that as we define, and that's exactly here, right? Yeah, and so well, this is under the condition that A is symmetric. So then we can write A in this way. So and so with that we can continue. and 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 so basically what we expect here is to have two components, right? So there is a sum, right? So because of and the first part of this sum will be exactly as the result of what we got in 151, but there will be also the second one that we need to transpose certain indexes, and the indexes that we are going to transpose here, okay, so they are related to this one, right? So that's the second part is transposed, right? So mn, so we'll have the m and n transposed here, so n will come here to I and m will be here in j, so we'll have two parts of that, right? Okay, so let's see what is the result. Basically, again, the first part is exactly the same as, okay, with the factor half here, so we take the derivative of a with respect to derivative of a, so of course we will get exactly the same by the same logic as here, and this term is coming from the derivative of a transpose with respect to a, and that came here with the transposition of m and n, so that was our definition for the transposition, and so m and n, you can see that they are, so they change their location here, so we have different delta ni and mj, and you can see the difference in the structure, and this is maybe not that obvious result of adding this constraint of the symmetry. But one of the conclusions here to say is that the result, the symmetry is of course preserved as we take the derivative here. So this is another important observation as we take this derivative. All right, so now let's do something really useful for us is with what we just did with this derivative of scalar tensor function with respect to a second order tensor. And what we're going to do is we're going to calculate the derivatives of this invariant, of the invariants of a tensor. And that will prove to be very, very useful in the continuation of the postulating how the material behaves and how we derive stress-strain relationship for soft materials. Now, here is just a reminder of the structure of our invariants, right? For second order tensor, so we have three invariants. First is simply trace A, right? Which is just the trace, the summation of the components that sit on the diagonal of that matrix from the components. The second invariant is also important one. They representing these quadratic terms, also in terms of trace. And so the third invariant is nothing but determinant. Now, so let us take these derivatives of all these invariants. So the first two, I1 and I2, will be pretty straightforward. So that will be quite quite easy for us to deal with. But for this, and you can already see because the traces can be written in terms of the components, and so it's quite easy for us to take the derivative as we defined it, right? And just to find the situation when the derivative of components with respect to components of A will be non-zero. So that you kind of can start seeing it already from here when it takes this derivative. Okay, so the I2 is a little bit more involving than I1, but still, so the structure is the same. Now, with the third invariant, it becomes a little bit trickier because then you have lots of thinking about the way how you would write the determinant. That will be quite a bulky expression that may not be that easy to to actually to take this derivative in a direct way and calculate. So it's a little bit tricky how we will derive the third invariant. But okay, let's deal with each of these one by one. Right. So with I1, so what we need to do is just to write our definition. Just as we already did, right? So and so remember we had that function f that was a scalar, so that now function f is nothing but akk. This is again a number, which is okay. So just a reminder, if we didn't get used to this by now, so when we have the repeating indexes kk, meaning that make it go with a summation of 1 1 2 2 and 3 3. So that is exactly this summation here. But nevertheless, this is just a scalar, just a number, so that's right here. And so when take a derivative with respect to tensor A, so this is our structure here, how we wrote it. This is how we also defined that what it would mean, right? Now, so you can immediately see that, okay, so we already used that property. So when we take the derivative of these components of the same thing with respect to the same thing, we obtain deltas, right? So there will be combination of deltas, right? When k equal to I and k equal to j, so we'll have two deltas, and that will ensure that the result is 1 and not 0. And so we'll have delta ki and we'll have delta kj. Now you already can say right away that, okay, so we'll have two deltas that will have the same index k, right? And that means that we can use the property of Kronecker delta, that if you see that it has an index that repeats somewhere here, so just what that delta does is it's just you come and replace that index with the one that was free, that did not repeat, right? So and either you think about this delta acting on this delta, then there is a k and this I will replace this k, or you think about this delta acting on that delta, so there is again k and this k, and so this delta will come and replace that k with this j, and the result will be delta ij or ji, and that's for Kronecker delta doesn't really matter, it will be exactly the same result. And but then if the delta ij ei tensor product ej, so what the result is that it's nothing that we have here exactly. This is the definition of identity second order identity tensor, right? So the delta ij ei tensor product ej. That's quite an interesting result, right? So we take the derivative and we obtain the of the first invariant with respect to f, and we or a second order tensor, and we obtain identity tensor here. Now for the second order tensor, we're going to do similar operation, right? But okay, so we'll have a little bit more components here that we will need to deal with, right? Okay, so the first component here is the okay, so this is just the square of trace A, so we just need to take this similar structure akk and multiply it with some other guy, I don't know, so with repeating indexes mn or nn. Now for trace of a square, so what happens is that all right, let me just use my skills in writing, and maybe I also will change the color. That will not be all right. So 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 I'm talking about this part here. So the first part is just okay, take the same thing, multiply it with the same thing, and so That's straightforward. So this is also straightforward, but I just feel that maybe we should actually do that. So, well, what we have here is, again, okay, trace a square. But I'm not writing a square, but rather writing a, right? So that's how they multiply each other. And so in terms of the components of this, so what we will have is that we'll have a, let's say it was I j, that is j, multiplied by a j, and say k. Okay, before we make it a trace, whatever is in the parentheses. But okay, if we want trace, let's put it here. So as a parenthesis here, okay, so the parentheses here come. And so to make it trace, so effectively you can call this whole thing of, I don't know, let's call it BIK, right? IK. And if I now, and if I now want to make this trace, so I will just say that, oh, okay, so the trace of BIK is nothing but it's just BII or BKK, right? II or BKK, and we can write, because it's repeating, we can write it any letter. So basically, effectively, we could write the trace of whatever is here inside is just this a, and I'm going to replace this index, so it will be repeating. So the trace make it in this way, right? So we have say I, and here j, and here a with j and I. So this type of summation. So and we need to do summation here, but the order of indexes is important. So I here and I here they repeat, and j here and j here they repeat. So and so that what will be here in the second term when we start to take the derivative. Okay, so let me return to this, and so that's what we wrote here. So the first one, okay, so it's again AKK multiplied by another trace. Okay, just we decided to use LL, doesn't matter, some repeating indexes, so one trace multiplied by another trace square, right? So the first term in I2, and so the second term here is just what I tried here to emphasize how it will be. So the because these indexes are repeating, we can write any index, any letters. They are dummy indexes, right? So the only what they represent is the summation. So instead of I, we had here M and M. An important thing is that they appear at the same at the right location, right? So the first one and the last one here, they are dummy M and M, and N and N. So they appear through this. Right? So this is the second term here, trace of a square, right? Or trace of the new matrix that is the result of multiplication of a and a. Okay, so now our so we need to do some work on that. So we actually now to go and we need to take properly this derivative one by one. So there is the first part here, so which we okay, let me go again to the okay, first I will just erase that, so we'll have a little bit more space that I can still use here. Okay. Okay, so and now we're going to take this derivative here, and and so we have this AKK. So let's call it the first term, right? So that this will be number 1. Okay, so let's start from number 1 here. Okay. And this is also the exercise that you probably should repeat too, and try to derive on your own. That is a good exercise. Right, so now we take that whole thing. This is a sign of partial derivative. Apologize for the not perfect writing again. Oh no, that's already too bad. And with respect to dAij. Right, so now we have and there is a factor of half that will carry that too. And so now so the rules here are very similar to, basically we have summation of these two. So first I take the derivative of akk with respect to aij, and then I multiply it with all, and then I basically take the derivative of all, and I keep akk as outside of the parentheses, so that they will have two terms. But because they're basically exactly the same, so it doesn't matter the kk, ll, they are the same, so these two terms will be identical. So now we can say, okay, so let's write them. So just explicitly what I said. So I just said, okay, let's take the first derivative of akk, the first term, and take it with derivative with respect to daij, right? And then I need to multiply it by what is left from the parentheses a. We said ll, right? And then plus now I take the derivative of all with respect to the same dij, and I multiply it with akk. But they will be exactly the same, so I basically have this factor 2 here after that. Right, and so now we know that if I take, and we just did that, write it here. So when I take this derivative of akk with respect to aij, the result will be nothing but delta ij. Okay, so one delta ki, the other delta kj, and so this, and then there are two deltas exactly as we just dealt with that. So there will be delta iij, delta ij here multiplied by all. And exactly the same thing will happen here too. We also have this delta ij multiplied by akk, but again all is exactly the same as akk, right? Because they represent trace as it was before, right? So akk. And so with that, we can write that with this factor half, we actually we have factor 2 here. So we can write that we have the first term produce nothing but so we have identity tensor, right? Delta ij together with ej multiplied by all or akk. But this is nothing but the first invariant. So the first thing that produces us, so this one will produce us at the end, will produce us I1, the first invariant, the trace, right? Multiplied in by, and here I probably will change the color to black to identify that this is bold. All right, so that is what did I say? Identity tensor, right? So this is to use I or sometimes or 1 like that. So that's the first part. All this multiplied by half produces I1, the trace multiplied by identity tensor. Okay, so now the second term with the minus has a different structure. All right, let me just erase it very quickly. Now the second term is right here. Okay. Okay, I'm going to change the color very quickly. Okay, so the second term, now we are going to take the derivative of this trace of the new tensor a square. And so, and again, this is a good exercise for you to also to practice on your own, to actually to see that you are comfortable with the indexes. And so we have here two things. We have here I just write it. So we need to take the derivative of mn and m with respect to daij, and again we're having here two terms. So I keep here n m out of the derivative, and then I need to add to that the other term when I take the derivative of a and m, right, the second one from this one with respect to daij, and I multiply it with the remaining amn, right, amn. And so now, as you can see, so yes, we are going to produce here some deltas, right? But we are not. So in here we still will have some indexes that. So okay, let's just do this one by one. So now this mi and j. So let's deal with this first part of that. So that will be again very similar. That will be delta mi, delta nj, right? So we have two of them, delta mi, delta nj, multiplied by a and m. And here we have delta ni, okay, right? So n and I here multiplied by delta mj, right, and multiplied by a m n. Now let's see what happens here. So again, you find the same delta here and m and m here. So m is going to replace that one, right? So right. So this m is going to come here and replace it with I, and that n is going to here and replace it with j, right? So the result of that here will be that will disappear, but that will produce j here, so that will be a j, and here will be, instead of m, will be I. So that's the first term that the whole thing produced here. Now the second term here, so now we come with this n, right, and make it I here, right? So again I will use it with a little different color, right? So this delta will come with this n, and will substitute instead of n I here, and this delta will come and act here on m to substitute that m with j in here, right? And so the resulting the result, of course, will be will be, as we said, a. so j here, I here, so that will be another a j I. So basically what we got here is 2 a j I, right? So okay, so this is the whole thing, right, in here. So the part 2 here is minus 2a, oh sorry, ji, of course, not ij, ji. This is important because then it makes it transpose. So this is ji. Ji. And so it's factor 2, this is factor half. So basically, instead of what we had here, we have the we have 2.5, so we have AGI. But AGI together with EIJ, that will produce a tensor A transpose. So and finally, we can write the result in a compact way, just like that. So remember, the first term we derived, it was identity tensor multiplied by trace A, some result AKK. So that's the first term that comes from here. And the second term we just derived it. So this is the minus here. The minus survived. We didn't touch it. It didn't change. But what we had in the second term, after a very simple manipulations and with deltas and taking the derivative, producing deltas, and then using the properties of Kronecker delta, we just realized that this derivative of the structure of this trace A square is nothing but A transpose. And so now you have the result of, if you want to take the second invariant of a second order tensor, the derivative of second invariant with respect to some tensor, so the result will be this identity tensor multiplied by some scalar, actually first invariant. That's very interesting, right? So in the derivative of second invariant, the first invariant will appear, but of course there's some logic behind this, and minus A transpose. The good thing about it, so once you derived it once, you basically can use this formula. You don't need to derive it anymore, and there are quite many times that you actually will need these derivatives, but you don't need to go through this process all the time. Having said that, this is again a very good exercise to practice your index notations and deriving this again, maybe after some time, or trying to do this on your own. But if you cannot do this, you can watch the part where I tried to derive it here together with you. Now the final thing that we will do, and that will be already tricky. So that here we need to do something a little bit more involving than just using this in the indexes and taking derivative and using the Kronecker delta properties to manipulate the result. Now, so for the third invariant, we will take a little bit unexpected and different approach. Now, again, so just what is the third invariant? It's nothing but determinant of A. So now that's where the problem comes from. How do we take the derivative? How do we write this in terms of the components? And how can we manipulate that? So that's what we will do next.